Okay, so let's get into this. We are doing a deep dive today into a concept that, honestly, it feels more like philosophy than physics at first.
Right. It feels almost made up.
It does. We're talking
Yeah.
about something millions of times smaller than an atom, but it's it's the reason the universe as we know it can even exist.
It really is the ultimate sort of hidden mechanism. It's why anything from the phone in your hand to, distant galaxies, why any of it has substance.
And that paradox is just so compelling. I mean, how can
Mm.
something so incredibly small, so fleeting, be in charge of something as massive as existence itself?
Hmm.
So we've taken the source material, all the articles on particle physics, the history, that 2012 breakthrough. And our mission today is pretty clear. We're going to unpack what the Higgs boson actually is, how it works, and why finding it was such a monumental deal for science.
And what's so fascinating, really, is that this particle, the Higgs boson, it's not important for what it is, but for what it represents. It's basically a little ripple, an excitation of the Higgs field.
That's the key distinction, isn't it? It's not just about one rogue particle.
Exactly. It's an entire environment, a field that's everywhere.
Okay, so not just a localized thing.
Not at all. You have to think of the Higgs field as this invisible, persistent energy field that just saturates all of space. I mean, every single corner of the universe is swimming in it.
So if this field is literally everywhere, what's its main job? What is it? What is it doing?
Its job is, well, it's monumental. It gives mass to fundamental particles. That's it.
It gives them mass.
It gives them mass. Without that one function, all the math, all the models of physics, they just completely fall apart. The difference between something having mass and not having mass is, the difference between matter and just pure energy.
Right, so how does it actually do this? It's not like there's a little scale out there weighing electrons.
Yeah,
Right?
no, I know. And this is where that famous analogy comes in, and you see it in all the sources because it just works so well. Imagine the Higgs field is like a thick invisible syrup or maybe mud filling up a room.
Okay, so it's something you have to move through.
Exactly. And when particles travel through this syrup, they encounter a kind of resistance, a drag.
Oh, like trying to run through a swimming pool instead of just walking down the street?
Precisely. That's the perfect way to think about it. And the amount of mass a particle has is directly tied to how much it gets dragged back by the field.
So it's a slowing down mechanism.
It is. The more a particle interacts with the Higgs field, the more resistance it feels. And that resistance, that drag, is what we perceive as mass.
Okay, that brings up a question I think a lot of people would have. If everything is moving through this cosmic mud, why are some particles massless? Like photons, particles of light.
And that's the really elegant part of the whole theory. Photons, they slip through the field completely. They don't interact with it at all.
So zero resistance.
Zero drag, zero resistance. So they're never slowed down. They always travel at the speed of light, and they have no mass.
So mass isn't something a particle has. It's something it gets from its interaction with the field. The more you get bogged down, the heavier you are.
That is spot on. A really heavy particle, like a top quark, interacts incredibly strongly with the field. It gets bogged down a lot, making it supermassive. It's the universe's speed bump that forces particles to slow down and, become matter.
This is where things get a little terrifying, actually. Let's do that thought experiment from the sources.
Yeah.
What happens if we just switch it off? Turn off the Higgs field.
Yeah, that's a big one. If
Yeah.
you could somehow just remove that field, that resistance, you'd be pulling out the entire scaffolding of reality.
It would be a catastrophe. I mean, a complete catastrophe for all matter.
Absolutely, because if the field vanished, all those particles, electrons, quarks, everything, they'd instantly become massless again.
And they wouldn't slow down. They'd just fly around at the speed of light.
And if they're all moving at the speed of light, they can't stick together. The whole way atoms work, with electrons orbiting a nucleus, that depends entirely on them having mass.
Right. Without mass, the forces that bind particles together just wouldn't work.
Yeah.
So not a single atom could form.
Not one. You wouldn't get nuclei, no chemistry, no elements. The universe would just be, well, like the physicists say, it would be just escaping energy.
A completely featureless cosmos of light and energy, and then nothing.
Pretty much. No stars, no planets, no you, no me, no structure at all.
And that really brings it home for you, the listener. It makes you realize how essential this whole thing is. Because this field exists, we have atoms. We have molecules, objects, planets. Your own body, the ground under your feet. It's all constant proof that the field is doing its job every single second.
It truly is the framework of our physical world. But for decades, it was just that, a theory, a guess. Scientists proposed it way back in the 1960s, but they had no proof at all.
And just think about that. 50 years, half a century of research. Why was it so unbelievably hard to prove something so fundamental to everything?
The problem was the particle itself. To even see a Higgs boson, you have to hit the Higgs field with a tremendous amount of energy. It's like trying to make a big splash in that ocean of syrup. You have to hit it really, really hard.
Of energy levels we haven't seen since the Big Bang.
Exactly. You have to, in a way, recreate those conditions on a tiny scale.
Which is where the Large Hadron Collider comes in.
That's the one. The LHC at CERN. A 27-kilometer ring built essentially to solve this one problem.
Can you just, I mean, the scale of that is mind-boggling. What were they actually doing in there?
They were taking protons and accelerating them to, it's just an absurd speed, 99.9999999% the speed of light, and then smashing them into each other head on.
Wow.
These weren't just little taps. They were creating collisions with just insane amounts of energy, more energy than any experiment on Earth had ever created before. They needed that overwhelming force to basically knock a Higgs boson loose from the field.
And after all that, decades of work building this massive machine, the discovery itself was, I mean, it was unbelievably brief, right? They didn't just find one and put it in a jar.
Oh, absolutely not. That's the craziest part. The Higgs boson is incredibly unstable. It exists for just an impossibly short moment.
So it appears, and then it's just gone.
Instantly, it appears and immediately decays into other, more stable particles. It's like a subatomic ghost.
So then how do you prove it was ever there, if you can't even measure it directly?
You look for the clues it leaves behind. It's detective work. Scientists were looking for its unique decay signature, specifically a pattern of 2 high-energy photons, 2 gamma rays. That theory predicted would be the footprint of a Higgs boson.
So they were looking for the wreckage.
Exactly, the debris trail. And when they saw that specific pattern over and over again with enough statistical certainty, that was it. That was the confirmation in 2012.
So that tiny, brief flicker, that was the proof for the most important theory in modern physics.
That fleeting moment confirmed everything. You see, before 2012, the standard model of particle physics, our best theory for, everything, had this giant hole in it.
It couldn't explain mass.
It couldn't explain mass. The Higgs was the final missing piece of the puzzle. Once they found it, the whole model just clicked into place. It proved the foundation was solid.
It proved the universe isn't just random. It has this incredibly precise mechanism for assigning mass to things.
Yeah.
And it works the same way everywhere.
Right. It's organized. And that precision is what leads to the deeper questions. If we can understand the Higgs even better, how it interacts with an electron versus a top quark, for instance, we might start to understand the very first moments after the Big Bang.
So understanding mass could be the key to understanding creation itself.
It's a new window into it, yeah. And the thing that scientists always point out, which I love, is that every time we discover something this big, we realize the universe is just stranger. It's more complex than we ever could have imagined.
I think that's the perfect takeaway, that the universe is always weirder than we think. It takes some real humility, doesn't it?
It really does. Because solving the Higgs problem actually created new ones. Like, we still don't know why the Higgs has the specific mass that it does. It doesn't quite fit with some other predictions, so more questions.
So to bring this all home for you, the key takeaway is this. Our entire physical existence, planets, our bodies, everything, it all depends on a particle that exists for less than a blink of an eye. A truth that was hidden from us until just over a decade ago.
And when you think about the monumental effort it took, those 50 years just to find something so crucial, it really makes you think about the knowledge gap.
If something so fundamental to our very existence was invisible to us until 2012,
Yeah.
what else is out there?
Exactly. What other essential pieces of reality are right in front of us doing their job completely outside of our awareness right now?
What other mind-boggling things are just waiting to be discovered?
The search goes on. That great big unknown is what keeps science moving forward.
And that's our deep dive into the particle that makes existence possible.